Hello everyone, and welcome to the first online lecture for Math 837. We are in week 10 and this is lecture 1. Okay, so first let's talk about some changes to the courses because of this coronavirus shutdown. The lectures will now be these online video lectures such as this one. The tutorials are now virtual tutorials, and the quizzes and the assignments will be posted as usual, but they will be collected via Crowdmark instead of in person. Details on the tutorials and the quizzes/assignments can be found on Quarkus. The office hours are now Thursdays 11 a.m. to 1 p.m. And they will be via Piazza. That being said, because the lectures are now online, it's more important than ever that you're proactive about asking questions on stuff that you don't understand. I will be online Thursdays 11 a.m. to 1 p.m. on Piazza, but I will also be checking regularly in case anyone has any questions. I will be able to answer that outside the office hours as well. The final exams, there will be no more in-person final exam. The details on that are to be announced. Okay, so let's start with a brief recap of where we were at before the shutdown. So we were talking about sequences. So we defined a sequence AK of real numbers as a function from the natural numbers to R. Examples of a sequence include just k equals 1, so 1, 2, 3, 4, so on. Or something more complicated like 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. And these are the most basic examples of sequences. Of course, a sequence can be any assignment of real numbers to the natural numbers. Okay, then we define the convergence of sequence. So we say that the sequence AK converges to L, or in other words, the limit as k goes to infinity of AK equals L if, for all epsilon greater than 0, there exists a natural number n such that AK minus L is less than epsilon for all k greater than n. Intuitively, this just means that as k gets bigger and bigger, the sequence AK gets closer and closer to L. We also defined what it means for a sequence AK to be monotonic. So we say a sequence AK is monotonic if it's either A, increasing, that's to say AK plus 1 is greater than AK for all k, or it's decreasing, that is to say AK plus 1 is less than or equal to AK for all k. We also had similar definitions for strictly increasing, where we replaced the inequalities by strict inequalities, and also eventually increasing or eventually decreasing. We then defined a sequence to be bounded if it is both bounded below and bounded above. So bounded above means that there's some number big M such that AK is less than or equal to big M for all k, and bounded below means that there's a little m, which is also a real number, such that AK is greater than or equal to little m for all k. Okay, so today we will be talking about the bounded monotonic convergence theorem. So first let's talk about the idea behind the bounded monotonic convergence theorem. So suppose we have a sequence AK, and suppose it's bounded. And also monotonic. And for the sake of example, let's say it's increasing, but it could also be decreasing. Right. So if I plot it out as a function of, k versus, so I have k over here, this is 1, 2, 3, 4, so on. And this is, of course, the y-axis is AK. Because it's bounded by big M and little m, let's call this big M here, and let's call this little m. So we know that it never goes below this little m line, and it never goes above this big M line. So it starts, say, somewhere, so A1 is something like this. And then A2, because it's increasing, it has to go upwards. And A3 is even higher, A4, and so on. So eventually, because it never goes past the big M, it will eventually either become constant, in which case it converges to that constant, or it'll approach M, getting closer and closer, in which case we can say that it converges to big M. In a nutshell, this is what the bounded monotonic convergence theorem says. It says that if we have a sequence that's both bounded and monotonic, so either increasing or decreasing, it will converge to something. Okay, so let me formally write out what the bounded monotonic convergence theorem says. It says that if a sequence AK is bounded, and remember, bounded means both bounded above and bounded below, is bounded and monotonic, then it converges. Okay, so let's start with a formal proof of the bounded monotonic convergence theorem. So proof. And we're going to split this up into two cases. So case one, where AK is bounded and increasing. So let M equal to the supremum of AK. And we know that the supremum of AK exists because AK is bounded, therefore it's bounded above, therefore there exists a least upper bound. So let me just write that down. Supremum exists because AK is bounded. And the most useful, or not the most, but one of the useful properties of supremums, that's the least upper bound as opposed to just any upper bound, is, so by property of supremums, or the least upper bounds, for all epsilon greater than 0, there exists some element an such that an is greater than m minus epsilon. This is a property of supremum that we've used before. In a nutshell, what it says is you can get arbitrarily close to the supremum of a set, or in this case a sequence, with the elements of that set, or in this case sequence. Okay, next we must use the fact that the sequence AK is increasing. So because AK is increasing, it implies that for all k greater than n, AK must be greater than AN. Right? And this is the same AN from the last slide, which we also said was greater than m minus epsilon. Sorry, this should be greater than or equal to. So this means that m minus AK is less than epsilon for all k greater than n. And this is just by rearranging the inequality from above. Now we also know that m is an upper bound for the sequence, which implies that m is greater than or equal to AK, which means that m minus AK is greater than or equal to 0. And whenever something's greater than or equal to 0, we know that it equals its own absolute value, therefore m minus AK equals m minus AK. Combining these facts, we get that therefore m minus AK is less than epsilon for all k greater than n. And this, of course, is the definition of convergence. We've shown that for all epsilon greater than 0, there's some n such that m minus AK is less than epsilon for all k greater than it. So this concludes the proof. We've shown that the limit as k goes to infinity of ak is equal to m. So this was one case where ak is bounded and increasing. Case 2 where ak is bounded and decreasing, because remember monotonic means either increasing or decreasing. So the case where it's decreasing is very similar, so I'm going to leave that as an exercise for you guys. See if you can mimic the steps we did here. The things that change are, instead of supremum, you use infimum, and of course the inequalities are flipped, but I'll leave that as an exercise. Okay, a few remarks about the bounded monotonic convergence theorem. First, note that it doesn't actually say anything about what the sequence converges to. The only thing it says is if it's bounded and it's monotonic, then the sequence will converge to something. But from the proof, we saw that if AK is bounded and increasing, then it converged to its supremum. Increasing. Then the limit as k goes to infinity of ak is equal to the supremum of ak. Similarly, if ak is decreasing, is bounded and decreasing, then the limit as k goes to infinity of ak is equal to the infimum, or the greatest lower bound of the sequence. Okay, so let's cover a really simple example. Let's look at the sequence ak equals 1 over k. And we want to use the bounded monotonic convergence theorem to show that this sequence converges. So pictorially, we've seen the sequence a few times before. Pictorially, if this is k and this over here is ak, we start at a1 equals 1, then it goes to a half, then 1/3, then 1/4, then 1/5, and so on. So you see it's getting closer and closer to 0, and it's bounded below by 0, and that's the pictorial reason of why the B and CT works here. But formally, first we gotta show that it's bounded. So because k is greater than or equal to 1, right, because we're only looking at the natural numbers, this implies that ak equal to 1 over k is less than or equal to 1. And also, because k is positive, and 1 is positive, then 1 over k must be positive. So we have that 0 is less than or equal to ak, is less than or equal to 1, and this is true for all k. Therefore, ak is bounded. Is bounded. And now we need to show that ak is, the sequence is monotonic. In this case, the sequence is decreasing, and the way we show that is we observe that k plus 1, so note that k plus 1 is greater than or equal to k. Well, it's strictly greater than, but for the sake of example, we'll say greater than or equal to. This implies that 1 over k plus 1 is less than or equal to 1 over k, which means that ak plus 1 is less than or equal to ak. Therefore, the sequence ak is decreasing, i.e. monotonic. And then by the B bounded monotonic convergence theorem, the sequence converges. And again, the BMCT doesn't tell us what the sequence converges to. We know that the sequence converges to 0, and by the remarks before, we know that the infimum of this sequence is 0. But for this problem, we're just happy that the BMCT tells us that the sequence does in fact converge to something. Okay, so now let's consider the converse of the bounded monotonic convergence theorem. That is to say, if a sequence converges, is it bounded and monotonic? So part of that is true. So theorem, if a sequence AK converges, then it is bounded. It's bounded. However, it is not true that it is also monotonic. But AK converges does not imply that AK is monotonic. And an example of that would be, so it does not imply. So example of this would be the sequence AK equals -1 to the k times 1 over k. So this sequence, if I draw it out, looks like this. So if I have 1, 2, 3, 4. So it starts at 1, then it goes to 1/2, then 1/3, then 1/4, and so on. So you see it's getting closer and closer to 0. So it does converge to 0. So AK converges to 0, but it's not monotonic. But AK is not monotonic. And I'm going to leave this as exercise to show that AK does converge to 0 and AK is not monotonic. But we can see that it's not monotonic is because it's going from positive to negative to positive to negative, which means that it's increasing, decreasing, increasing, decreasing. So it's never strictly, never always increasing or always decreasing. So given what we know up till now, let's see how we can use the bounded monotonic convergence theorem and its converse to show that various sequences diverge or converge. So we're going to start with a sequence, let's say AK equals e to the k. And the question is, does AK converge or diverge? Converge or diverge? So note that this sequence is in fact monotonic. So AK is increasing because of course e to the k plus 1 is always greater than e to the k. However, AK is not bounded. And of course this is because e to the k goes off to infinity. A good way to show this would be to note that if there was a sum bound m, so AK is not bounded because for all m that are natural numbers, e to the m is greater than m. For all m greater than 1, greater than or equal to 1. So this shows that if there was some upper bound, well, e to the m is greater than m, therefore m cannot be an upper bound. So from this, can we say that AK converges or diverges, or neither? Well, recall the theorem about if it's convergent, then it's bounded. So if AK was convergent, it would be bounded. And the contrapositive to that statement is because AK is not bounded, so because AK is not bounded, it can't be convergent. It can't be convergent, therefore it's divergent. So therefore AK diverges. Okay, so let's do another example. So example, let's consider the sequence AK equals K over E to the K. And the question is again, does AK converge or diverge? Or can we not say converge or diverge? So again, we want to use bounded and monotonic properties of the sequence. So first let's see if this sequence is bounded. And note that it's bounded below by 0 because K and E to the K are both positive. Right? So that means their fraction must be positive. So this implies that 0 is less than or equal to K over E to the K, which is equal to AK. Also note that K is less than or equal to E to the K for all K greater than 1, greater than or equal to 1. This implies that K over E to the K is less than or equal to 1. Or in other words, AK is less than or equal to 1. So therefore, AK is bounded. It's bounded below by 0 and bounded above by 1. Now to see if AK is monotonic, we're going to use the derivative test. So AK is in fact decreasing by the derivative test. And recall the derivative test says that by the derivative test. So derivative test says that if AK equals f of k, and in this case f of x is a function x over e to the x. Sorry, e to the x. So if AK equals f of k, where f is some function that's differentiable, if the derivative of f is less than 0, then the sequence is decreasing. In this case, f prime of x is equal to minus e to the x times x minus 1, which is less than 0 for all x greater than 1. So this implies that, so therefore, the sequence AK is monotonic and it's bounded and bounded. Therefore, it converges. Converges. Again, we don't know what it converges to because that's not what the bounded monotonic converges theorem tells us, but it tells us that it does converge to something. You can actually show that this sequence converges to 0, but that's for some other time. Okay, so the last example we will cover is AK equals cosine of pi k over k. And again, the same question, does it converge or diverge? or diverge. So right off the top, we know that this sequence is bounded. So AK is bounded because cosine is bounded between -1 and +1. So that means that -1 over k is less than or equal to cosine over k, which is less than or equal to 1 over k. And of course, -1 over k is bounded below by -1, and 1 over k is bounded above by 1. So this implies that -1 is less than or equal to ak, which is equal to cosine pi k over k, is less than or equal to 1. However, note that this sequence is not monotonic. So the sequence is, if we look at A1 is just equal to -1 over 1. So A1 equals -1 over 1. A2 equals 1 over 2, so 1/2. A3 equals -1/3. A4 equals 1/4. So the sequence goes from negative to positive to negative to positive. It goes up and down, which means that it's not monotonic. So AK is not monotonic. So we have the sequence is bounded, but it's not monotonic. Can we say if it converges or diverges? So the bounded monotonic convergence theorem says that if it's both bounded and monotonic, it converges. Therefore, we can't say it converges. Also, it is not true that if the sequence converges, then it has to be monotonic. So in this case, we cannot say whether the sequence converges. So we can't. Therefore, we can't say if AK converges or diverges. Of course, this is only using bounded and monotonic properties. You can actually use the squeeze theorem that we covered last lecture to show that this sequence does indeed converge to 0. But as far as the bounded monotonic convergence theorem goes, it's not useful here. So that's everything for today. Thank you for watching. Again, this was much more dense than in-person lectures, and I was not able to stop for questions. So if you do have any questions, please post them on Piazza. I will check regularly and answer them as soon as I can. Thank you.